Greetings and welcome to Distilled. In this video, we'll be discussing a few more concepts involved in entropy. Entropy change of an isolated system. So when we talk about an isolated system, we can treat it as one which is made up of system and its surroundings. So altogether, that would make up an isolated system. So the entropy change for an isolated system is always greater than or equal to zero. All right. This is the rule for an isolated system. That means the entropy change for a system plus its surroundings, this would make up an isolated system, is always greater than or equal to zero. Okay. So this is in general. This is a very general concept. Okay, entropy change for a system plus entropy change of its surrounding is greater than or equal to zero. Okay, so this entropy change is actually equal to zero in case of a reversible process. So if the process is reversible in nature, then the entropy change of the system plus surroundings will be zero. And the reason behind that is that you people already remember in the first lecture of elementary thermodynamics, we discussed about reversible and and irreversible processes. So when we talked about an irreversible process, so we discussed that let's say I want to go from state A to state B through an irreversible process. Then it's actually a direct and a very fast process, right? It takes place very rapidly. However, if it is through an through a reversible process, then in that case, we'll follow steps, right? We'll follow steps and there would be infinitely many steps. And each step would be an equilibrium state, right? Each step would be an equilibrium state. And this way you'll reach state B. So since we are moving from an equilibrium state to another equilibrium state, which is so close to the first equilibrium state, therefore the entropy change is negligible. All right. The entropy change is negligible in that case. All right. So for transfer from one equilibrium state to another, which is so close to each other, the entropy change goes zero throughout. All right. So that is why entropy change in the first, while it moves from first equilibrium state to the next one, it's zero. And next to next, zero. Next to next, again, zero. So that way it goes zero. Throughout, the entropy change remains zero. Therefore, for the next net process from A to B, the entropy change becomes zero. All right. So the reason behind this is that we move from one equilibrium state to another, and that equilibrium state is so close to the previous equilibrium state that the entropy change is zero. So that is why for a reversible process, the net entropy change becomes zero. Okay. For an irreversible process, the entropy change is always greater than zero. Okay. The increase in entropy is due to the internal irreversibilities of the system. This increase in entropy is also referred to as entropy generation. All right. So in case we are moving from A to B, which is an irreversible process, this is an irreversible change. So entropy in whatever the entropy is exhibited in state A, there would be some entropy generated, which will take it to entropy of B. All right. So this entropy that is generated, it is due to the internal irreversibilities of the system. All right. So since there would be some internal irreversibilities in the system, this entropy has been generated, making the entropy of state B greater than that of state A. And hence the net change in entropy becomes positive. All right. So let's move on to this particular problem. 1 kilogram of superheated steam at 1.5 megapascal and 523 Kelvin with these as the properties is contained in a piston cylinder assembly. The unit is kept at ambient conditions of 300 Kelvin and the steam condenses to saturated liquid, which is this at constant pressure. What is the change in entropy, and check whether the process is reversible or not. So let's understand this question. So first of all, our system is basically 1 kilograms of superheated steam in the piston cylinder assembly. So let's say this is my piston cylinder assembly. So this is my piston cylinder assembly, and here I have 1 kilograms of steam. All right. And then we have the surroundings. We have its surroundings, which is maintained at an ambient temperature of 300 Kelvin. All right. The ambient temperature of these surroundings is 300 Kelvin. Okay. So now we have to evaluate the entropy change. So basically, entropy change for the total system is going to be entropy change for the system. That is, this is the system. And then the entropy change for the surroundings. So these are your surroundings. All right. So for calculating the entropy change of the system, we are seeing that the initial entropy is 6.71 and the final entropy is 2.32. So the net change in entropy in the system is the final entropy, that is 2.32, minus the initial entropy, that is 6.71. So this is going to be equal to minus 4.39 kilojoule per kg Kelvin. All right. And since we are considering just 1 kilogram of steam, so this is going to be like this. All right. So this is the entropy change of the system, minus 4.39 kilojoule per Kelvin. Okay. Then in order to calculate the entropy change of the surroundings, we have to keep this in mind that heat is transferred to the surroundings, right? Heat is transferred to the surroundings. So since heat is transferred to the surroundings, so by the definition of entropy, we have this as dq by t, right? Entropy change would be integral of dq by t. And since heat is entering the surroundings, if we consider the surroundings, then heat is being entered into the surrounding. Heat is input to the surroundings. So that is why heat is going to be positive. All right. So whatever the heat is released by the system, that heat would be gained by the surroundings. So heat released by the system would be equal to 845 minus 2923.5, right? Since it's at constant pressure. Now keep in mind, this enthalpy change is coming as negative because heat is going out of the system. But the same heat is being accepted by the surroundings. So we'll take positive, that is 2923.5 minus 845. Okay, because this is what is accepted. This is negative because we are this heat is leaving the system. But since we are considering surroundings over here, surroundings are accepting this heat. That is why it's going to be positive. So it's going to be 2923.5 minus 845. And the surroundings are accepting this heat at a temperature of 300 Kelvin. So we'll divide this thing by 300. So the entropy change is going to be plus 6.928 kilojoule per Kelvin. All right. Then we are going to find the total entropy, that is surroundings plus system, 6.928 minus 4.39. That is equal to 2.538 kilojoule per Kelvin. All right. So now this is the total entropy change, which is positive. Hence, the process is irreversible in nature. All right. The process is irreversible in nature. This is the first thing. Second thing, this process is going to be spontaneous in nature. All right. The process is going to take place. The process is going to be spontaneous in nature. All right. And the third thing that you can get from this is that the process will take place on its own, right? The process will take place on its own. So this is what we have got from the entropy change. All right. Then we move on to the next problem. Two compartments, each of 1 meter cube capacity, are connected by a valve and insulated from the surroundings from each other. One compartment contains saturated steam at 683.6 kilopascal, and the other contains steam at the same temperature but at a pressure of 101.3 kilopascal. All right, the temperature is the same, but the pressure is different. The valve is open and the pressure is allowed to equalize. Determine the change in entropy of the system consisting of the two vessels. Comment on the irreversibility of the system. Okay, and this is the data that has been given to us. All right, so we'll solve this problem. So we have two compartments. Compartment number 1 and compartment number 2. All right, these are the two compartments. In the first compartment, we have pressure as 683.6 kilopascal. We have temperature. Now, the saturation temperature is 437.2. So that's going to be the temperature over here. So that's 437.2 Kelvin. All right. Then over here, the pressure is 101.3 kilopascal, and the temperature is going to be same, 437.2 Kelvin. Okay. So we have the data, all the data that is required. We have it from over here, right? So we'll get specific enthalpy, internal energy, specific volume, and entropy, right? Entropy of the system. So we'll have all these things. So specific enthalpy is given to be 2761 kilojoule per kg. All right. Specific volume is given to be 0.2789 meter cube per kg. Then internal energy is 2570.4 kilojoule per kg. And entropy is 6.7133 kilojoule per kg Kelvin. All right. Similarly, we can get enthalpy, specific volume, internal energy, and entropy for the second case as well. Right? So we have all this information. Okay. Now we'll find the mass that is present in each case. All right. So we know that volume of each compartment is 1 meter cube, right? So the volume of compartment 1 is 1 meter cube, and the compartment 2 is also 1 meter cube. And we have the specific volumes of the steam present in both cases. So we'll get M1 as 1 upon V1, right? 1 meter cube upon the specific volume. So that would give us M1 is equal to 3.585. Okay. Meter, sorry, not meter cube, kg. This is 3.585 kg, and M2 is going to be 1 upon V2. So that is 0.506 kg. All right. So the total mass is going to be M1 plus M2. So when this partition is removed, then the total mass of the steam that is present in the compartment is going to be 3.585 plus 0.506. That is 4.091 kg. That is the total mass. Okay, this is the total mass that is present inside this. Okay. Now, once we have all this information, then we'll find the specific enthalpy. Specific enthalpy. See, we already have the total mass, so we can definitely calculate the specific volume of the final steam that is present after mixing. So that is going to be 2, that is 1 plus 1, 1 meter cube plus 1 meter cube upon the total mass. That will give us the specific volume. right? That will give us the specific volume of the total gas, that is 2 meter cube, when this compartment is, the separation is removed, and the total mass is 4.091. So we'll get the specific volume from it. So specific volume is 0.489 meter cube per kg. All right, we have this. Then we'll have to calculate one of them, H1, enthalpy or internal energy or entropy, anything, any one we can calculate. And based on that, we can see that what state are we in. So let's calculate the specific enthalpy. The specific enthalpy is M1H1 plus M2H2 upon total volume, total mass, right? This we get from energy balance, right? So when we do that, we get the enthalpy as 2766.318 kilojoule per kg. All right, this is the specific enthalpy. And temperature is going to be the same as these two. That is 437.2 Kelvin. 437.2 Kelvin, right? So from the steam tables, we'll go to the steam tables, and at a temperature of 437.2 Kelvin, we'll see at what pressure do we get this as the specific volume, and we'll verify with H, that do we get H equal to 2766.318 at this condition or not. So we'll go to the steam tables, we'll find temperature is equal to 437.2 Kelvin. All right. Then we'll search for which pressure do we have such that the specific volume would be 0.489 meter cube per kg. And at which pressure do we get enthalpy is equal to 2766.318. All right. So we'll find this out. So from the steam tables, what we get is that this pressure is equivalent to 400 kilopascal. All right. This pressure is equal to 400 kilopascal. Okay. So on the basis of that, we can at 400 kilopascal, when we go to the steam tables and find this pressure as 400 kilopascal and temperature as 437.2 Kelvin, then we'll find that what is the entropy at that condition. All right, we'll find out what is the entropy at that condition. So the entropy at this point comes out to be 6.999 kilojoule per kg Kelvin. All right, this is the entropy. So that is why the change in entropy becomes the total entropy of the system. In the initial case, that would be M1S1 plus M2S2. That is the initial case. So change in entropy would be S minus the initial entropy, that is M1S1 plus M2S2. Okay. So when we solve this, S is equal to 6.999 and we have S1 and S2. So when we solve this, we'll get the net change in entropy as 0.68 kilojoule per kg Kelvin. So this is the entropy change when this is removed, right? When the partition is removed. So this is the entropy change within the system, right? This is the entropy change within the system. So this is delta S for system, right? Then we'll find the entropy change for surroundings. So for the surroundings, as we can see that it is insulated from the surroundings. Okay, the two compartments are insulated from the surroundings. That means no heat loss is allowed, right? No heat loss is allowed. Since there is no heat exchange with the surroundings, therefore the net change in entropy for the surroundings is 0. Therefore, the total entropy change is going to be entropy change of the system plus entropy change of the surroundings. That is going to be 0.68 kilojoule per kg Kelvin. This is positive. We had to find whether the process is irreversible or reversible. So the process is irreversible in nature. All right. Then we talk about entropy change in irreversible processes. All right, let's talk about this slightly in more detail. All right. So now we'll go back to our basics, that is Carnot engine, from where we actually started. Okay. So when we talk about a Carnot engine, for a Carnot engine, which operates between high temperature reservoir and low temperature reservoir, right? So from here, QH, W, and QL, right? Now, efficiency of a Carnot engine is basically W by QH, which we all have, we all know that this is equal to 1 minus TL by TH, right? Or this can be said as TH minus TL by TH. This is the efficiency of the Carnot engine, all right, which is equal to work upon QH. So in that case, work done can be written as QH times TH minus TL upon TH, correct? This we'll take as equation number 1. Okay, this we'll take as equation number 1. Now, when we talk about an irreversible process, all right, let's talk about an irreversible process such that in this irreversible process, we have a high temperature reservoir, we have a low temperature reservoir, and heat is being transferred from this high temperature reservoir to the low temperature reservoir. Okay, so when we talk about this irreversible process, then in this case, the entropy change is going to be entropy change of the high temperature reservoir. So since it is losing heat, therefore minus QH by TH, correct? And then plus the entropy change of the low temperature reservoir. So it is gaining heat. So it is plus QH upon TL. All right. So from here, we'll get this as QH into TH minus TL upon TH TL. Right. So that is what we get. Right. This is the entropy change. This is the entropy change for an irreversible system. Okay. This is the entropy change for an irreversible system. Now, this we'll take as equation number 2. So for a reversible system, this is the amount of work that you can get. Okay, this is the amount of work that you can get. So for this, we'll get W for a reversible system is equal to QH into TH minus TL upon TH into TH minus TL upon TH. And what we'll do, we'll multiply and divide this by TL, right? So QH into TH minus TL by THTL is basically the entropy change for the irreversible process, right? So this can be written as TL into delta S, right? This can be written as TL into delta S, okay? So this has to be kept in mind. So if the process would have been reversible in nature, if the process would have been reversible in nature, then this is the work that you would have got. All right, this is the work that you could have extracted. However, the process is irreversible in nature. Since the process is irreversible in nature, that is why this is the work that is lost. Okay, this is the work that is lost. So the work that is lost due to the irreversibility of the system is equal to temperature of the heat sink multiplied by the entropy change of the system. All right, that is the work that is lost. Okay, that is equal to the work that is lost in case of an irreversible process. Okay, so whenever we are supposed to calculate the lost work, so the lost work is equal to TL into delta S. All right, TL into delta S. Keep that thing in mind. Okay, so with this, we'll move on to our next problem. Hydrocarbon oil is to be cooled from 425 Kelvin to 340 Kelvin at a rate of 5000 kg per hour in a parallel flow heat exchanger. Cooling water is supplied at this rate and the mean specific heats are given. We have to calculate the total change in entropy, and after that we have to uh, see that if the if a reversible Carnot engine is to be operated, receiving the heat from the oil and rejecting heat to the surroundings at 295 Kelvin, how much work would be available? All right, so let's solve this problem. So first of all, we have to see that we are talking about a heat exchanger. So therefore, we need to first of all conduct an energy balance. Okay. So now, since hydrocarbon oil is being cooled, cooling water is going to gain heat. All right. So heat lost by oil is equal to heat gain by water. And we need to take mod of both, right? For energy balance, we need to take mod of both. So let's say the final temperature of cooling water is T. Then in that case, we are going to say M oil into Cp oil into delta T for oil is equal to M water into Cp water into delta T for water, right? So M oil is given to be 5000 kg per hour. So 5000 into Cp oil is 2.5. Delta T for oil is 425 minus 340 is equal to M water is 10,000 kg per hour. Then the higher temperature in case of water is going to be T because it is gaining heat and rising to a temperature of T. So 4.2 into T minus 295. All right. So this is the energy balance. So from here, we'll get T is equal to 320.3 Kelvin. Okay. This is what we'll get as the temperature. Okay. Now, determine the total change in entropy. So the total change in entropy is equal to the change in entropy of the system plus change in entropy of surroundings. So in case of heat exchanger, the system is going to be oil and the surroundings to which it is actually losing heat is going to be water, right? So this is going to be delta S for oil plus delta S for water, right? And we are going to say that the process is taking place at constant pressure. So that is going to be equal to MCP ln T2 oil by T1 oil plus MCP, this is M for water, Cp for water, into ln T2 water upon T1 water, right? So this is going to be delta S oil and this is going to be delta S for water. So when we individually calculate the delta S for oil is going to be 5000 into 2.5 into ln. The final temperature for oil is 340 Kelvin. So 340 upon initial temperature for oil was 425 Kelvin. So delta S for oil comes out as minus 2789.3 kilojoule per Kelvin. Okay. And for water, for water, we get this value as 10,000 into 4.2 into ln. Final temperature attained is T, that is 320.3, upon initial temperature is 295. So this value comes to 3455.87 kilojoule per Kelvin. Okay, that is delta S for water. So the net change in entropy, the total change in entropy comes as 666.57 kilojoule per Kelvin. Okay, this is the net change in entropy. Now this change in entropy is positive. Therefore, the process is not reversible. All right, the process is not reversible. This is the first part. Then the second part states that if a reversible Carnot engine is to be operated, receiving the heat from oil and rejecting the heat to the surroundings at 295 Kelvin, how much work would be available? So let's talk about this. So we are talking about a reversible Carnot engine. So for the Carnot engine to be operable, we have a high temperature reservoir. We have heat lost from that reservoir. That heat would produce some work and the remaining would be disposed of to the surroundings. Right? The remaining would be disposed of to the surroundings. For the Carnot engine, we know that QH by QL is equal to TH by TL. Right? QH by QL is equal to TH by TL. Now, the heat that is received is basically from oil. Okay, so heat received from oil, that is QH, is equal to M oil, CP oil, delta T for oil. So that is 5,000 into CP for oil into delta T. That is 425 minus 425 minus 340. Right? So that is going to be the heat lost, or basically the heat that gains from oil. So that is 1062500 kilojoule per hour. Okay, that is QH. Okay, then TH, obviously we don't know, right? And TL is given to be 295. So you know that QH by TH is basically the change in entropy of the high temperature reservoir. All right, it is the change in entropy of the high temperature reservoir. And since this is heat lost from the high temperature reservoir, therefore this is going to be negative, right? Negative of the change in entropy that is observed. The change in entropy is observed, that is minus 2789.3. Therefore, QH by TH is going to be equal to 2789.3 kilojoule per Kelvin, right? This is QH by TH. And now we have QH by TH from this equation. QH by TH is equal to QL by TL. Hence, QL would be 2789.3 into TL, and TL was 295 Kelvin. So into 295, that gives you QL as 822,843.5 kilojoule per kilojoule per hour, right? So now by energy balance, you'll have QH is equal to W plus QL. Therefore, the work that is obtained from here is QH minus QL, which is going to be around 2.4 into 10 to the power 5 kilojoule per hour. All right, this is what is there. This can be done using another method. We know that the B part. we know that the process is reversible, right? We know that the process is reversible. Therefore, the net change, the total entropy change is going to be 0. That means entropy change of system plus entropy change of surroundings is going to be equal to 0. What is the system? The system is oil, right? The system is oil. So entropy change of oil, we calculated it as minus 2789.3 kilojoule per Kelvin. Okay. And the entropy change of surroundings is going to be QL upon temperature of the surroundings, right? That is going to be the entropy change of surroundings. So temperature of the surroundings we know as 295 Kelvin, right? So when we substitute all this over here, we'll again get QL is equal to whatever we got, 822,843.5 kilojoule per hour. And using that, we'll get W as again 2.4 into 10 to the power 5 kilojoule per hour. Okay. So this is what we have. Okay. So both ways you can solve this problem. You'll get the same thing. Now we move on to the last problem of today's video. Oil of specific heat, 3.2 kilojoule per kg Kelvin, is cooled from 495 Kelvin to 315 Kelvin at a rate of 5000 kg per hour by exchanging heat with a large thermal reservoir at a constant temperature. What is the lost work in process? So we know that the lost work is equal to the surrounding temperature into entropy change, right? Entropy change of the system. Okay. The total entropy change, right? So the total entropy change is going to be equal to entropy change of system plus entropy change of surroundings, right? Now let's talk about entropy change of system. So system is oil. So MCP T2 by T1, right? So that is 5000 CP is 3.2 ln. Final temperature is 315 and initial temperature is 495. So entropy change of the system comes as minus 7231.762 kilojoule per Kelvin. Okay. And entropy change of surroundings is equal to heat lost to the surrounding, that is heat added basically to the surroundings. So that is mod of MCP delta T for oil upon temperature of the surroundings. Okay. So that is 5000 into 3.2 into 495 minus 315 upon temperature of the surroundings is 300. So this temperature change, entropy change of the surroundings is 9600 kilojoule per Kelvin. All right. So the total entropy comes as 2368.24 kilojoule per Kelvin, which gives us lost work is equal to 2368.24 into 300, which is the temperature of the surroundings. That is 7.1 into 10 to the power 5 kilojoule per hour. All right. So that's how you calculate the entropy change and the lost work. All right.